Okay, good morning again, Denmark and Noriel. So before we start the last module for the course, yay, last na. All right. So just housekeeping matters. So mukhang matatapos natin today yung module 11. So we will really have a buffer week next week, which could serve as your So siguro first I'll give you the problem set, the second problem set for the course on December 14th, all right? And the deadline would be on December 21st, the last day of classes. I think that's a Tuesday, right before midnight. So yun yung kailangan yung gawin. And then we still have lab exercise number 7, which will pertain to the contents of module 11. So yun yung gagawin nyo by December 13th sa lab. Kaya last lab exercise, December 13th. And then the problem set will be given December 14th. You will have 1 week to finish the problem set. So ang deadline niya ay December 21st. So again, I advise you guys to take hold of the previous programs that you wrote for lab exercises kasi baka magamit nyo siya sa problem set number 2, right? Because I'm going to review what your lab instructors ask you to do in the lab exercises. And if I see some butas or some discontinuities dun sa flow ng discussion na gusto kong i-assess kung talagang naintindihan nyo, siguro mag-a-add ako, aside from some minor theoretical questions, I'll put some application problems in the problem set. Okay? And then also, after December 21st, we'll also have, actually, hindi pala after December 21st. So we also have a final project, which is, I think, worth how many points? That's worth 20 points or 20% of your final grade. The deadline would be during the finals week. I'll give you the final details, or I'll give you a detailed document laying out the guidelines, the idea, the rationale behind the final project. So, yun, bibigay ko siya next week. Kasi buffer week naman tayo next week. So, pwede nating i-discuss yung gagawin yung project. Malaki-laki yung chunk ng grade na magagaling sa project. It's 20%. So, I hope you guys put your best for it to compensate for probably kung nahirapan kayo sa mga lab exercises o sa mga problem sets, time yun na para bumawi. The deadline would be during the finals week. I'm still thinking whether to make it twofold. There's a written report and then a final presentation. All right. So, pero titingnan ko yung schedule kung kakasya during the finals week. And of course, I don't want to burden you too much during the finals week kasi baka may iba pa kayong mga kailangan gawin during the finals week come January. But I'll think about it over the weekend and I'll give you the final guidelines next week. So for certain, ang schedule natin next week, December 13th, Lab Exer 7, which is wala pa dun sa Module 11 na in-upload ko. Kakasend lang sa akin ng draft ng Exer. I'll take a look at it and upload it later tonight or early tomorrow para masimulan nyo rin if you want. And then the problem set will be given December 14th at 8 a.m. It will be due December 21st at right before midnight, 11:59 p.m. And then next week, we can meet probably at least once to talk about the final project and if you have some questions about the problem set. Okay? So I hope that's okay with you guys. All right. So today, we'll tackle the last module for the course, Module 11, which is about Monte Carlo integration. Though the discussion I wrote for the module is quite lengthy, meron akong mga sinabing theoretical points and so on, but I wish to finish the coverage of Module 11 today, so probably I'll skip some of the conceptual things about the Monte Carlo simulation, like its advantages over the quadrature rules and so on. So I will assign good portion of Module 11 as a reading assignment to you guys. What I'll try to do now is to discuss the implementation of the Monte Carlo simulation together with the motivation or what you call this, the idea behind the method itself para mag-guide kayo kung bakit ganito yung algorithm o bakit ganito siya ini-implement. So the focus now will be more of the process itself and the implementation and not its technical nitty-gritty. But I'll try as much as possible to insert as much as possible today para hindi na ganun karami yung kailangan yung balikan from Module 11. Okay? Now, what is Monte Carlo simulation? Well, basically, The numerical integration techniques that we have developed in the previous modules are heavily reliant on the given data points or the choice of set of abscissas. And in such a case, we can say that they are deterministic. Bakit sila deterministic? Kasi pag binigyan ko kayo halimbawa ng isang fixed data set, meron kayong mga x's at mga f of x's na binigay sa'yo. Kung gagamit ka ng Newton-Cotes quadrature rules, right? At gagamitin mo lahat ng data points na binigay sa'yo. That means, di ba ang idea sa Newton-Cotes, kukunin natin yung interpolating polynomial na daraan doon sa lahat ng data points na binigay sa atin. Alright? And the unisolvence theorem tells us na unique lamang yung makukuha kong interpolating polynomial para dun sa data points. So meron akong unique polynomial na makukuha na pang approximate sa data. Pag in-integrate ko yon, makakakuha ko ng isang unique approximate for the integral of the function represented by the given data points. So kaya siya deterministic. Fix yung data na binigay sa'yo, isa lamang yung makukuha natin na function na approximate para sa integral. Given a complicated function and you want to use the Gaussian or the Gauss-Legendre quadrature rules, pag nag-isip ka ng isang degree of precision, nakapag-decide ka na okay, gagamit ako ng endpoints that will give me a quadrature rule of degree of precision to n minus 1. Ibig sabihin, meron akong mako-compute na fixed set of abscissas and weights associated to those abscissas. But nevertheless, when I implement the Gauss-Legendre quadrature rule, I will still get a unique approximate for the value of the integral. All right? Nakapag-decide ako, endpoints yung gagamitin ko, meron lang akong isang unique na answer na makukuha gamit yung Gauss-Legendre quadrature rule. All right? Now, that's a big contrast to what we'll discuss today, which is Monte Carlo integration. It's non-deterministic. In other words, it's probabilistic kasi nga random drawing ito ng data yung gagawin natin. So this works best if you have either a large pool of data na ayaw mo namang gamitin silang lahat para dun sa numerical integration mo kasi imagine you have, say, 1 million data points. So kung meron mo 1 million data points, pag Newton-Cotes quadrature formula yung gagamitin mo, simple Newton-Cotes ang gagamitin mo, ibig sabihin nagkakaroon ka ng degree 999,999 na polynomial, which would be very wiggly, very oscillatory yan. So magiging biktima tayo ng Runge phenomenon. So, at saka mahirap mag-integrate ng degree 999,999 polynomial, right? Even if it's a polynomial, though the machine can handle it, pero meron pa ring strain dun sa computational machinery na gagamitin natin, right? So, baka hindi rin ganun maging ka-accurate yung gusto nating data points. Lalo naman kung Gauss-Legendre yung gagamitin nyo. Kasi kung Gauss-Legendre yung gagamitin nyo, gagamit ka ng 1 million points. So, ibig sabihin, hanapin mo yung 1 million associated weights para sa kanila. Alright? So, malaki rin siyang problema from the point of view of the Gauss-Legendre formula. So basically, sa quadrature rules, pag masyadong marami yung points, mahirap na siyang i-implement. Alright? So sa Monte Carlo simulation, this is ideal if you have lots of data points, though ayaw mong gamitin silang lahat in one go. Alright? So kaya siya probabilistic kasi pipili lang tayo ng certain fraction or certain part of the data set. Tapos i-run natin yung simulation several times and then we will appeal to the law of large numbers to get the best approximation. All right? Kaya isa siyang hit or miss kasi ito ay probabilistic nga. So hit or miss, depende sa bunot mo ng data points, yung pagiging maganda ng approximate na makukuha mo. Kaya siya tinawag na Monte Carlo simulation. Right? So, but Monte Carlo simulation is a generic term that is not only used for integration. Pwede siyang gamitin sa kahit anong numerical experiment that you do several times using random variables. All right? So, na-develop siya ni John von Neumann saka ni Stanislaw Ulam during the Second World War when they're modeling uncertain conditions. Tapos niraran nila yung different scenarios and they are averaging out the results of their simulations to get the what they think would be the best approach or ano yung optimal policy that they can employ during the Second World War. Kaya lang hit or miss nga ito. It's either you get a very good approximate or you don't. We don't have any big control on the data set. So probabilistic nga siya. Kung anong mabunot mo, yun yung gagamitin mong data set. So ibig sabihin talagang parang nanguhula tayo. Pero this will hinge, the idea is hinged on the central limit theorem or the law of large numbers. Na sinasabi na if you do the experiment a large number of times, then the uh, the results that you will get will be closer and closer to the expected value. So, pag meron kang process na ginawa involving random variables, gawin mo yung experiment, say, 1,000,000 times, then the results or the average of the results you'll get will be close to the expected value. All right? Halimbawa, sa coin toss, the chance when flipping a coin once, there's of course, assuming you have a fair coin, flipping it uh, flipping it will give you a 50% chance of getting a head or 50% chance of getting a tail, right? So pag flip mo yan two times, posibleng dalawang heads yung makuha mo. And that would be actually that would be a miss kasi hindi ka nakakuha ng 50-50 result, right? Pero ang sabi ng central limit theorem, intuitively, o ng law of large numbers, if you perform the experiment a lot of times, say I flip the coin say 100 times, then it is most likely that the number of heads will be around 50, right? It would be better, it would be closer to half if I will flip it more times, say 1,000,000 times, then I'll get heads around 500,000 times. So ganun yung parang idea sa Monte Carlo simulation. Let's perform the simulation using as many data as possible and we will eventually hit the mark. We will eventually get a good approximate for our integral. Okay. And then, isang pang bentahe ng Monte Carlo simulation over the deterministic quadrature rules is that they do not suffer from instabilities caused by non-smooth integrals. So dun sa last discussion natin, which I apologize, I forgot to upload it in YouTube, yung integration anomalies, and some of you had some troubles accessing the video recording. Baka yung mga walang team. Sorry about that. I completely forgot about it before I left last Thursday. So it's already up in YouTube, and I think one of the lab instructors posted it using Google Drive last time. So yeah, I apologize for that, but you can watch the video now. Hopefully, hindi malaking inconvenience yung nangyari when you did your lab exercise last week. All right. Now, going back, hindi siya yung Monte Carlo simulation dahil function value evaluation lang siya. All right? Walang involved na weights dun sa calculations. So, hindi siya gaanong nagiging naapektuhan ng mga non-smooth integrands. Kasi yung error bound sa Monte Carlo simulation or yung pag-exist na order derivatives ng integrands, unlike the quadrature rules. All right. Moreover, it is not too much hampered by the complexity of the integrand. When I say complexity of the integrand, probably it's about the ease of computing its antiderivative or its derivative. Okay. So pero kapag ka-komplikado yung integrand mo in terms of the number of operations required to evaluate function values, then posibleng yung Monte Carlo simulation ay mahirapan rin. Kasi function evaluation yung ginagawa sa Monte Carlo. But that thing is shared among all quadrature rules. Kasi kung mapapansin nyo, lahat ng mga numerical integration techniques na ginagamit natin, lahat sila ay nakadepende sa function evaluation. Right? Thirdly, is that dahil sa pagiging simple ng algorithm ng Monte Carlo simulation, hindi siya naapektuhan ng dimensionality ng problem. So ibig sabihin, yung accuracy niya, right? O yung level of yung quality of results niya ay hindi naapektuhan kung one-dimensional, two-dimensional, three-dimensional, or four-dimensional yung integral na ine-evaluate natin. Kasi hindi katulad sa quadrature rules sa napaka-reliant niya doon sa number of variables doon sa integrand. Okay. Halimbawa, mag-i-integrate tayo ng function of two variables. All right? Tapos sinabi natin na gagamit lang ako say ng 100 points. Function of two variables, 100 points. So ibig sabihin, yung 100 points na yon, okay, kailangan ko siyang piliin along the x-axis and along the y-axis. Halimbawa, ito yung integration interval omega. A, B, C, D. Nag-integrate ako along x. Ang ine-evaluate ko ay integral from A to B, then integral from C to D of f of xy dy dx. Halimbawa, ito yung ine-evaluate ko. So, nandito ako sa region na to. Okay? Tapos sasabihin ko, ang kaya lang ng computer ko ay 100 points yung gagamitin. So, kailangan mong i-allot yung 100 points dun sa mesh o dun sa pagkuha mo ng discretization nung integration rectangle natin. That means, if you want equal weights on the discretization along the x and the y-axis, yung interval AB hatiin mo sa 10 points o 10 interval. Alright? Then yung interval CD, hatiin mo rin sa 10 points or sa 10 intervals para makuha mo yung total na 100 points. Kasi you discretize it 10 times along the x-axis, 10 times along the y-axis, 100 points. And basically, dahil nagtipid ka dun sa discretization points, dun sa bawat axis, ibig sabihin malaki yung value ni h. Remember, h is the step size. Gaano kalaki yung pagitan between two x values or between two y values. Sa pagpalagay nating equal yung haba ni AB at saka yung haba ng interval CD, and then ibig sabihin yung h mo ay length of AB over 10, which is quite big. And remember, the order of convergence of quadrature rules is dependent on the step size h. Right? So, lalo na kung 3D. Kung 3D, halimbawa, gagamit ka ng 1,000 points, then sa 10 lamang. Sa x, sa y, at saka sa z-axis, yung magagamit mo na data points which will make your h very large. Right? Compared sa Monte Carlo simulation, sa Monte Carlo simulations, ang error estimate, right, ay hindi nakadepende sa step size. Kasi there's no point of talking about step sizes in Monte Carlo simulations kasi nga sa Monte Carlo simulation, random nating pinipili yung data points. So hindi tayo nagdi-discretize, basta bumubunot tayo ng mga points dun sa integration interval or sa integration area or integration region, omega, right? So, ang sinasabi niya, hindi ko na i-derive, hindi na natin i-derive, pero galing lang to sa central limit theorem, yung error estimate sa Monte Carlo simulation ay laging proportional sa 1 over square root of n. Right? It's the total number of data points used in the simulation. So, ibig sabihin, kung gusto mo ng error which is around which is about 10% lamang. So kailangan ang kunin mo ay 1 over square root of 100. So you need to use 100 points regardless if you are in 1 dimension, 2 dimension, 3 dimension, and so on. Kasi nga yung error proportionality constant is not dependent on D. It doesn't depend on H because there's no H in Monte Carlo simulations. So nakadepende lang siya sa number of data points used. Right? Now, nag-enumerate ako dito ng ilang bullets ng advantages ng Monte Carlo simulations, pero meron siyang isang malaking disadvantage. Napakabagal ng order of convergence ng Monte Carlo simulation, especially for low dimensions. Yun yung problema niya. Right? Napakabagal kasi nga hit or miss siya. So kahit sa one-dimensional integral, ang hirap makakuha ng result that is accurate, say 10 to the minus 3 or with relative error of 10 to the minus 4 lamang. Right? Pero ang kagandahan sa kanya ay habang lumalaki yung dimension ng problem, mas gumaganda yung result mula sa Monte Carlo simulation. Alright? Tingnan natin tong example na to. Meron akong diniscuss dito which involves the composite Simpsons rule. The composite Simpsons rule is of order of convergence 4. That is, the error vanishes in the composite Simpsons rule as fast as how h to the fourth approaches 0. Right? Yung error laging proportional sa step size raised to the 4. Okay? Now, sa Monte Carlo simulation, sinabi nga natin na lagi lang 1 over root n. So i-compare natin kailan nagiging magkasing bilis yung convergence ng composite Simpsons rule at saka ng Monte Carlo integration. I mean, saang dimension nagiging magkasing bilis sila ng convergence. Alright? Now, going back to the composite Simpsons rule, halimbawa, sa composite Simpsons rule, hahatiin ko bawat coordinate axis into n subintervals of equal length. Alright? So, n subintervals sa bawat coordinate axis. Halimbawa, d dimensions or d-dimensional yung problem. So, ibig sabihin, kung sa bawat coordinate axis, meron akong n points or n subdivisions na gagamitin, I will have n to the power d points na gagamitin doon sa buong dimension. Kasi bawat isa dun sa d na coordinate axis, hatiin ko into n subintervals using n points. So basically, dahil sa bawat axis, sa bawat axis, meron akong n points. So ibig sabihin sa buong integration region, I will have n to the power d. So let's call n to the power d equal to capital N. So gagamit si composite Simpsons ng capital N points, gagamit din yung Monte Carlo simulation ng capital N points. Tingnan natin ano yung dimension d kung kailan magiging magkasing bilis sila. Alright? Now remember, the composite Simpsons rule has the order of convergence h to the 4th. So yung behavior ng errors sa composite Simpsons rule ay katulad ng behavior ng h to the power 4 or proportional sa behavior ng h to the power 4. Alright? Pero ano yung h? Yung h siya yung step size sa bawat coordinate axis. Remember, we divided the coordinate axis into n subintervals of equal lengths. So, ibig sabihin, yung value ni h ay 1 over n. So, h equals 1 over n will give us h to the 4th equals 1 over n to the power 4. All right? And then, I will translate it to capital N kasi ang error proportionality constant ng Monte Carlo ay nakadepende sa total number of points. Yung little n, number points lang yan sa bawat subintervals. Yung capital N siya yung number of points sa buong integration region. Now, we already let capital N to be n to the power d. So this guy can be written as 1 over capital N to the power 4 over d. Right? So ito yung error proportionality constant ng composite Simpsons rule. Now, I want to solve d so that this guy will be equal to the proportionality constant in the error for the Monte Carlo simulation, which is 1 over root n, which is independent of the dimension. All right? So ito yung sa Simpsons, tapos ito yung sa Monte Carlo simulation, and if you compare this guys, 4 over d must be equal to 1/2, we get d equals 8. So ibig sabihin pala, para matapatan ni Monte Carlo simulation yung composite Simpsons rule, dapat nasa 8 dimensions ka or higher. So ibig sabihin, kapag ka 8 variables yung nandun sa integral mo, saka lamang worth it na magpatuloy with Monte Carlo simulation rather than composite Simpsons. But there's a big caveat there, ang usapan magkasing dami ng points yung gagamitin natin. Yung comparison natin dito ay everything held constant aside from the dimension or only with the dimension as the degree of freedom. I mean, parehas yung number of points na ginamit natin sa composite Simpsons at saka sa Monte Carlo. Kung parehas yung number of points na gagamitin, dapat nasa dimension 8 tayo para halos magkasing bilis sila. For lower dimensions, composite Simpsons rule with capital N number of points will be better than a Monte Carlo simulation with the same capital N number of points. So makikita nyo, napakabagal ng order of convergence nung Monte Carlo simulation. Kasi nga, kailangan pang nasa 8 dimension tayo para sumabay siya sa composite Simpsons. Alright? However, there's a nice way on how we can compensate for this spectacularly slow convergence of the Monte Carlo simulation. Now, pwede rin natin siyang gamitin in lower dimensions, pero in the first place, pwede natin gawing si n napakalaki na kagad. Because we are not hampered by the problem of, say, integrating the Lagrange basis polynomial kung gagamit tayo ng Newton-Cotes quadrature rules, or the problem of solving a nonlinear system of equations to get the associated weights for the Gauss-Legendre integration formulas. Kasi, di ba, ang hirap i-compute ng weights. I guess some of you had some problems in one of the lab exercises na pinaderive yung degree of precision, yung 5-point Gauss-Legendre. So nagkaroon kayo ng 10 by 10 system ng nonlinear equations. Tapos hindi na yata siya kinaya ng MATLAB natin kasi yun nga, napakamahal ng symbolic calculations. Yung numerical schemes na sa Math 175 pa. Sa Mathematica, kaya siyang isolve yung 10 by 10 nonlinear system pero magtatagal din siya about 5 or 6 minutes bago niyo makuha yung sagot. Alright? So, mahal yung paggamit ng quadrature rules. Pero sa Monte Carlo simulation, lagi lang tayo nag-a-average ng mga function values times the area of the integration interval. So, hindi malaking deal yung paggamit ng napakaraming points. Sa Gauss-Legendre, mahirap na yung gumamit ka ng 5 points. Pero sa Monte Carlo simulation, hundreds of thousands, even millions or tens of millions of points to get a nice approximate. All right? So, hindi masyadong malaking problema yung paggamit ng malaking number of points sa Monte Carlo simulation. And actually, that is ideal kasi nga gumagamit tayo ng law of large numbers dito. You want to use as many points as possible. So, ang tanging kalaban lang natin doon yung computation time at saka yung RAM ng ating mga computer. But that's another issue. Nasa hardware implementation na siya. Right? So far, I'm just laying the foundation of Monte Carlo simulation versus quadrature formulas na sinabi ko reading assignment na lang. Hindi ko napigilan yung sarili kong ikwento sa inyo. But if you want more of the details, siguro baka may nakalimutan ng 1 point or 2, kindly read the discussion in the module. All right. Now, because now I'll focus more on the implementation of the process. First, let's consider this quick example. Paano nga ba nag-work yung, ano yung idea behind Monte Carlo simulation or Monte Carlo integration? Let's consider the problem of evaluating the integral of 1 over x squared plus 1 dx over the interval 0, 1. Now, this is just the antiderivative na 1 over x squared ay arctan lang naman. So you can get the exact value, which is pi over 4. Right? So sa Monte Carlo simulation, ang gagawin natin, pipili tayo ng mga random points. So technically, what we'll do is to pick randomly distributed numbers over the integration interval. All right? Tapos kukunin ko yung function values nila. Right? And then for each of these this x's, I will get an approximate for the integral by considering the area of the rectangle formed by the function by the actual interval 0, 1 and the function value of the chosen x. Tapos yun yung magiging approximate ko dun sa integral. All right? So ang ginawa ko dito, bumunot ako ng 5 points. Randomly distributed from 0 to 1 kasi yun yung integration interval. Now, the integral or the value of the definite integral that we want to generate is the area of the region shaded blue in this figure. Yung figure na nasa top left, right? Yan yung area to be approximated. Now, unang bunot ko, unang pili ko ng random number, ito yung nakuha ko, 0.506190. So ang gagawin ko ngayon, itong x sub I na to, itong x sub 1, kukunin ko yung function value at that chosen x. Tapos i-draw ko yung rectangle using the function value of x1 as the height. Ito yung function value ni x1. Alright? And then if I will calculate the area of this rectangle, yung shaded orange, alright? Ito yung magiging unang approximate ko para dun sa integral. Right? And visually, you can say na, mukhang swerte tayo ng bunot kasi yung area nung orange rectangle is almost equal, at least visually speaking, dun sa area ng kulay blue. Kasi although dito meron tayong underestimate, hindi natin sila nasama sa bilang, pero halos kasing laki yon nung overestimate natin dito sa kanan. So I will say na medyo hit yung napili ko na x sub 1 na unang approximate. Now, if you're just doing Monte Carlo simulation using 1 point, then the area of this rectangle would have been your approximate for the integral. All right? Sinulat ko yata kung ano yung nakuha ko dito. Okay. Now, ang estimate na yun ay 0.796034, which is, I think, is close to pi over 4. Ang pi over 4 ay 3.14 over 4, so that's about 0.75. So I'm going to say this is a good approximate. It was kind of a hit kasi maganda yung nabunot ko na x1. But of course, you will not do Monte Carlo simulation by just picking up 1 point. All right? Now, kasi halimbawa, ang nabunot mo ay ito. Ito yung nabunot mo na random number, 0.945600. All right? Kinuha mo yung function value, andito siya. And you see that this is a horrendous approximate to the area of the blue region. Kasi nga, napakalaki nung underestimate, hindi natin nabilang itong colored blue na to. Tapos, ito lang yung overestimate natin, nakatiting lamang compared dun sa hindi natin nabilang. Alright? But nevertheless, ito yung nabunot ko. Alam natin na pangit siya, pangit yung approximate na ibibigay niya. Pero kung wala tayong idea kung ano yung ina-approximate natin, if we are doing this experiment blindly without knowing what the area to be approximated is, then hindi natin alam na mali ito. Alright? Or pangit yung ibibigay niyong approximate. But nevertheless, the area will be our approximate. Okay? So, this is a miss. Hindi maganda yung approximate niyang ibibigay. So, sa Monte Carlo simulation, ang gagawin natin tong experiment na to hundreds or thousands of times. We will get the average of all the approximates. All right? And that would be our reported approximate for the integral. Kasi sabi ng law of large numbers, pag kinuha mo yung area ng napakaraming rectangles and you take the average of them, ibig sabihin, dapat maganda yung makuha mong approximate. Alright? Meron ka mga hits, meron ka mga misses, but they will all average out towards the expected value, which is the actual value of the integral. Alright? Now, I continue this experiment and drew 3 more points. Ito yung mga nakuha ko sa kanila. So again, kung papipiliin ako with this data, syempre ang pipiliin ko ay ito. Alright? But again, if we are hitting in the dark, hindi natin alam kung ano yung gusto nating i-approximate. So, ibig sabihin, ang safe bet with the law of large numbers in mind, kunin ko yung average ng rectangle na to, o kunin ko yung average ng areas ng rectangle na to, neto, average nilang 5, yun yung i-report ko as my approximate for the area of the blue region over here. And if you do so, all right, we'll get 0.0754291, all right, which only have an error of 3.98%. Okay? So medyo maganda na siya kasi in most applications, in physical applications, an error of 5% is still good. Even 10% nga sa engineering, okay pa rin sa kanila. So kaya medyo reasonable na siya. And mind you, gumamit lamang ako ng 5 draws dito. Alright, napaka-simple ng method. 5 draws lang yung ginamit ko. Now, if a lesser error is wanted, we can increase the number of draws. Halimbawa, dito sa figure, pwede kong damihan yung draws na gagamitin ko. Halimbawa, gumamit ako ng 10 draws. Medyo pumangit pa yung error kasi pag kinuha ko yung average ng areas ng 10 rectangles, galing dun sa 10 random draws, ang error na ay naging 4.5%. Pag 20 draws, naging 8% na, right? But if I do 20,000 draws, order 10 to the minus 4 na yung relative error. Alright? Pero makikita nyo yung mabagal na convergence dito. Kasi imagine, from 100 draws, we have 1.6% error. Alright? So 100. Pag ginawa mo siyang 10,000, so ibig sabihin ilan yung nadagdag? Nag-multiply ako ng 100 more. Yung error ay nasa 3.08 times 10 to the minus 4 pa lamang din. Alright. Hindi siya ganun kabilis katulad nung order of convergence nung mga quadrature rules natin last time. Alright? Kasi nga, napakabagal ng order of convergence ng Monte Carlo simulations. Alright? So just to give you an idea how the data points look like, dun sa 100 points na ginamit ko, right, pinlot ko dito yung mga dots, yung mga function values na ginamit ko. So imagine, ito yung mga dots na ginamit ko. Pag dumarami yung dots na ginamit ko, ang mangyayari ay yung mga rectangles na makukuha ko o yung average, yung areas ng mga rectangles na nabunot ko will really approximate the area of the region bounded above by the curve. Kaya mas okay na mas maraming points yung ginagamit. Kasi nga random yung pagpili natin ng mga data points. The more ika nga sa ano, ika nga the more entries, the more chances of winning. So parang ganoon yung nangyayari. Para mas malaking chance na maganda yung approximate natin, gumamit tayo ng mas malaking Monte Carlo simulation or mas malaking data dun sa Monte Carlo simulation natin. All right? Now, let's see. Okay, so any questions so far? So that's basically the idea of how do we do the Monte Carlo simulation. So let me know if you have questions about it before we go to the formal discussion of the algorithm. Though, yun na nga, sana nagka-idea na kayo kung paano siya gagawin. In the next few texts, i-discuss ko lang kung ano yung formal procedures. Pero nabanggit na rin natin siya kanina. Pero i-step by step lang natin siya ngayon. Okay, so I take your silence as a no. Okay, so in general, halimbawa gusto nating i-evaluate or i-approximate yung integral ng isang function of several variables. Halimbawa si capital X, ano yan? Multiple variables, x1, x2, x3, x4 hanggang xd kung d-dimensional yung problem. Tapos mag-i-integrate tayo over an integration region omega, which is a subset of r to the d. So pwedeng one-dimensional integral yan. Kung one-dimensional integral yan, yung omega ay open interval lamang. Kung siya ay double integral, iterated double integral, so si omega ay isa lang rectangle, right? Interval AB cross interval CD. So kung siya ay three-dimensional, magiging isang cubic lamang yung integration region natin unless you define a sophisticated surface of integration, but that's beyond the course. So yeah, yun yung i-consider natin. It's any dimension, all right? Now the first step is to select a value of capital N, the number of points that you will use. Ito rin yung una yung sasabihin sa program nyo. Gaano karami yung gusto mong gamiting data points doon sa selection mo. All right? So just keep in mind that the error will be proportional to 1 over root N. Pero yun nga, dahil Monte Carlo simulation yan, hit or miss yan, para mas mag-guarantee mo na yung error ay within your specified tolerance level, right? Huwag mong saktuhin na 1 over root n equals yung error tolerance mo na epsilon. And bago gusto mo 10%. So gagawin mong epsilon ay 0.10%, 0.1. Tapos hanapin mo lang si n. Hit or miss ito. So ibig sabihin, may makuha minimum value ni n. Capital N. Pero yun yung best case scenario. Kung malas ka sa mga raffle, so ibig sabihin kailangan mo taasan na si n. So i-times 10 mo, i-times 100 mo yung n na makukuha mo kung nag-expect ka ng 1 over root n na proportionality constant ng error. Alright? And then the second step is to draw a sample. Right? So magda-draw ka na ng random numbers or ng random members or random points doon sa omega. Alright? So halimbawa, meron ka lang interval AB. Okay? So gagamit ka ng n points, nakapili ka na ng n, capital N. Pipili ka ng n na random points from a uniformly distributed set of random variables over the interval AB. Now, kung sa MATLAB kayo gumagawa ng programs nyo, right? Ang syntax sa pagtawag ng random number ay RAND. R-A-N-D, tapos size nung random number na gusto mong kunin. Right? Pwede nyo gawing 1, capital N, Yung dalawang numbers dun sa loob ng rand, ibibigay niya kung ilang rows at ilang columns yung ibibigay niya na random numbers. Right? Kasi yung MATLAB nga ay nakabase siya sa isang matrix vector system. Right? So halos lahat sa kanya tinitreat niya as vectors. So etong rand, magbibigay siya ng 1 by capital N vector of random numbers from 0 to 1. Okay? So this is a 1 by N vector of random numbers from 0 to 1. Open interval yan. Okay. So may problema tayo kapag yung gusto nating integration interval ay A comma B. Kasi nga yung rand command para kay MATLAB, binibigay niya lamang ay mula sa interval 0, 1. So kailangan niyo siyang i-translate using a translation formula. So gawin mong A plus B minus A times the random number. Para yung sagot na to ay maging random number between A and B na. Right? So, ito yung starting point plus the length of the interval times the random number between 0 and 1. Ito yung kailangan yung i-translate kapag gamitin na formula kapag ang integration interval or kung saan nyo gustong bumunot ng random numbers ay hindi interval 0 to 1. I'm not sure about Python kung paano siya nagko-call ng uniform random numbers. Paki-check na lang sa documentation or sa help ni Python. Baka mas madali doon na rand tapos talagay mo lang sa pagitan ng aling dalawang numbers yung gagamitin mo na random number, right? Pero mas familiar ako kay MATLAB, ito yung gagamitin yung syntax. Okay? Now again, this should be independent observations of a random variable that is uniformly distributed. Okay? Tapos, pag nakapili ka na ng mga random numbers, ipapa-evaluate mo kay MATLAB o dun sa programming software mo, yung function value dun sa mga random elements of omega na napili mo. Right? Tapos, kukunin mo yung average ng mga function values. Okay? Yung average ng mga function values, yan yung average ng mga heights na kino-consider natin. Tapos, i-multiply mo yung average na yon by the volume ni omega. Right? So parang dun lang siya sa open interval AB. Right? AB. Tapos meron kang function. Ang nangyayari ay, di ba dito ay kukunin natin yung function value dun sa isa nating draw. Diba? Sa random draw, random ith draw natin. Tapos kino-construct natin yung rectangle. So pag kinuha ko yung area ng rectangle, it's gonna be the height, which is f of x by, times the length of the interval. Ito yung tinatawag natin na v. Alright? In our case, si v lamang naman ay b minus a. So ito yung size ni omega, yung volume ni omega. So one dimension length lang siya ng integration interval. So ito yung approximate natin using one instance of the simulation. Tapos ang gagawin natin, kukunin natin yung average. So isasum ko siya over lahat ng I, tapos i-divide ko by the number of observations. So ito yung average ng mga areas ng mga rectangles. Then you can play around this. Si b minus a ay constant, pwede ko siyang ilabas. Ang tamad kasing magsulat. So ilalabas ko siya, magiging b minus a times the interval, over the average of the function values. Tapos papalitan ko lang si b minus a, siya yung size ni omega, gawin ko lang siyang v. Kaya ganito yung formula na ito. Kapag ka nasa 2 dimensions ka na, si omega mo na ay rectangle. So si b dito ay magiging area na ng rectangle. Magiging area nung rectangle of integration. So dun sa example na integral from a to b, integral from c to d, siya ay magiging, si v ay equal sa sa d minus c times b minus a. Ano yung area ni omega kung saan ka nag-i-integrate? Right? Kung 3-dimensional si omega, kukunin mo yung volume ni omega. Kung 4-dimensional siya, kukunin mo yung volume ni omega, and so on. Alright? Now, magpapaalam na ako guys na medyo mag-overtime ako para matapos natin yung coverage ng Module 11. Konti na lang naman siya. I'm gonna talk about two concrete examples, example 1 and 2 in the module. Kaya lang baka lumampas ako ng 9:30. So I will understand if you guys have to leave by 9:20 or 9:30, lalo na kung may mga klase kayo nakasunod. Go ahead, leave, and then I'll just stay here. Kung walang matitira, okay lang naman. I will continue monologuing here. Tapos balikan nyo na lang yung recording later. Alright? Para bago kayo mag-exer, para makita nyo yung example na ginawa ko. Pero, yeah. You can stay if you want, if you don't have anything else to do. Kung di pa kayo tapos mag-almusal, then samahan nyo na lang ako. But, yeah, I'll understand if all of you have to go. Alright? So let's consider one example here, which I call a wiggly example, because you see the function x times sine x cubed, which is pictured in figure 11.4, is very wiggly. Napaka-oscillatory nung function na to. And using little points, which could be the case, or little number points, which could be the case for the Newton codes and the Gauss-Legendre quadrature rules, will not give us a good approximate for the integral. Kasi napaka-oscillatory ng behavior niya sa part na ito. So try natin itong tingnan or i-approximate yung integral ni f over the interval 0 to 4 using Monte Carlo simulation. All right? And I enumerated here 4 or actually 5 scenarios. Okay? Tingnan na lang natin isa-isa sila. All right? So unang scenario, pipili daw ako ng 100 points. Gawin ko yung Monte Carlo simulation with capital N number of points. So ang gagawin ko, bubunot ako ng 100 randomly distributed x's. Kukomputing ko yung function values nila. Tapos ito yung mga nabunot ko. Alright? Medyo minalas ako dun sa bunot kasi makikita nyo parang nagkumpul-kumpulan dito yung mga data points na nakuha ko. Which is not ideal because there's a very nice behavior over this portion of the graph. Alright? Dito ako nagwo-worry kasi napaka-oscillatory ng behavior. So I was hoping that in my draw, I will have many representatives on the, say, the interval 2 to 4. Kasi nandun yung medyo tricky na behavior ng function. Kung alam ko na ganito yung itsura ng function, then pwede ako mag-redraw ng mga data points. Alright? Pero kung hindi natin alam na ganito yung behavior ng function, then mukhang magiging hindi ganun maganda yung approximate using these data points that we have drawn. Alright? But nevertheless, it is what it is. These are the 100 points that I drew. So ngayon, kukomputin ko yung summation ng f of x sub I over all I from 1 to n. I'll multiply it with the area of omega. Ang omega lang natin dito ay interval 0 to 4. So v is equal to 4. Kasi ang v dito, kasi one-dimensional lang siya, siya yung haba ng integration interval all over 100, which is the number of points used. And if you do that, and actually I did this and I got 1.017, which is very huge compared to what the actual value is. The actual value again is around 0.35 or 0.36. Pero ang nakuha kong approximate using 100 points is 1.02. Right? The relative error is a glaring 284.23%. But I kind of expected this result kasi dun sa plotting pa lang ng graphs, duda na ako na maganda yung ibibigay nung Monte Carlo simulation using just 100 points. Okay? Oh, but by the way, I would like to remind you that this is a probabilistic approach. Every time nagdo-draw tayo ng random numbers. So if you will be recreating these examples on your own, iba yung makukuha nyo na values. Pwedeng mas maganda, pwedeng mas pangit, kasi random yung iba-iba tayong napipiling random numbers. Pare-parehas yung capital N natin, pero iba-iba yung mga exabytes na nakukuha natin. So pwedeng mas swerte kayo na yung makukuha yung points ay mas concentrated dun sa oscillatory part ng graph. That will give you a much better approximate than the 284% error that I got here. Who knows? All right. So yun yung isang scenario. So wag magpanic kung ibang-iba yung makukuha nyo na result. Alright? Okay, so yun yung experiment number 1. 100 points. I drew bad points, so I got bad results. Now, again, Monte Carlo simulation, pwede mo naman damihan kaagad yung number of points. Kasi nga, function evaluation lang yan, i-average mo yung function values, i-multiply mo by the size of the integration interval. That's all. That's what Monte Carlo simulation is. Now, I'll use 25,000 points. Okay. Now, using the run with 25,000 points, I got this approximate value for the integral. I got around 0.42. And the relative error now is down to 17.68%. And that is still not good, pero that is a lot better than the 284% error that we had before. All right. So yeah, more number of points, more chances of getting better approximate. Okay. Now, experiment number 3. Ulitin ko yung simulations. 25,000 sample points pa rin yung gagamitin ko. So, nag-approximate ako. Pangalawang draw. Siyempre, ibang 25,000 points na yung makukuha ko. So, iba na yung estimate na makukuha ko. So, on the second attempt, using a Monte Carlo simulation with 25,000 points, I got an answer or an approximate which is within 5% of the actual value. And you see, it is a better hit than the first draw that I got. Right? And then, ginawa ko pa siya ng pangatlong beses. Ito yung nakuha kong approximate. Oh, 6.68% yung relative error. Then, I drew one more time. Problema ko, mas lumaki yung error. Naging 10.84% na. And then, I drew one final fifth time. I got something that is extremely good. The error is just 0.71%. So less than 1% na yung relative error using my fifth draw. Okay? Now, if you know the exact value, which is absurd, kasi nga kaya mo siya na-approximate kasi hindi mo alam yung actual value, pero kung may idea ka or kung ito yung data na alam ko, syempre ang pipiliin ko yung I5 kasi siya yung may pinakamababang relative error. Pero in practice, hindi natin alam kung ano yung actual value. So there's no way we can compute the relative error. So hindi natin to makikita. Wala yan. All right. So ibig sabihin, eto lang yung makikita natin. How do I decide which of these guys will be the best? Each of them are obtained by using 25,000 points. All right. Hindi ko alam sino yung pinakamaganda sa kanilang 5. So ang gagawin ko na lang, law of large numbers, siguro mas okay na i-average ko na lang yung 5 sagot na yan. All right? And then I am betting on the law of large numbers that average, the average of the results of the Monte Carlo simulations will give me a good estimate for the integral. And true enough, the IAVE, which is the average of all these 5 runs, gave me a 0.36 approximate, which is accurate with only an error of 1.58%. And that's not too bad. All right? So, yun yung isang strategy. Pwedeng yung lakihan yung number of points. Kung medyo duda ka pa dun sa nakuha mong approximate, mag-run ka pa ng several instances. Draw the same number of points every time, or pwedeng damihan mo yung draw. Instead of 25,000, use 50,000 on your second draw. In the third draw, use 50,000. Fourth draw, use 100,000. And then you can average all of those draws and get and report the average as your approximate for the integral. And again, that line of thinking follows the law of large numbers. Okay? Now, kung meron ka namang idea kung ano yung itsura ng function na gusto mong i-approximate, halimbawa, nag-scatter plot ka ng mga data na binigay sa'yo, or alam mo talaga yung function, wala nga lang siyang closed form antiderivative, so kaya hindi mo siya ma-solve by hand, or masyado siyang komplikado, pwedeng gawin mo ay stratified sampling. Okay? So, tingnan ko siya dito. Ayan. So, inulit ko yung unang experiment. Gumamit ako ng 100 points. Pero yung 100 points na yon, dahil alam ko na oscillatory yung behavior, dito sa, tingnan ko nga yung instruction. Mhm. Okay. So dahil ito yung gusto kong gawin sa number 4. So gagamit pa rin ako ng 100 data points. Okay? Pero dahil alam ko na napaka-oscillatory ng behavior ng function over the interval 2 to 4, so pwede ako mag-stratified sampling, alright, ng mga random points. So ibig sabihin, dahil hindi naman gaanong controversial yung paggalaw ng function f sa interval 0 to 2, pwedeng dito ko i-allot 10 points lamang. Kaya siya stratified sampling. Meron kang subsampling na ginagawa over certain parts of the integration interval. There's no big fuss about the behavior of the function f on the interval 0 to 2, so might as well allot few number of points in the draw to be over that interval. So halimbawa, pipili lang ako ng 10 sa interval 0 to 2, and I will concentrate 90% of the points allotted for me, say 90 points, doon sa oscillatory part ng function, say on the interval 2 to 4. And you see the presence of more dots dun sa interval 2 to 4 rather than the interval 0 to 2. Ito ay pwede niyong gawin pag may idea kayo ano yung itsura ng function. Saan mas problematic yung behavior ng function, doon ako mag-aalat ng maraming samples. Tapos dun sa medyo smooth naman yung behavior niya or non-controversial yung paggalaw niya, konti lang yung points na i-assign ko dun sa interval na yon. Okay? Now the result is actually this 0.53, which has an error of just 46.75%. I used the word just kasi dun sa unang time na nag 100 data points tayo, 284% yung error. Pero introducing a simple stratification of the random numbers used, bumaba yung error by how many? By 5 times or around 4 times? So down to 46.75%. Okay? So kung gano'n naman pala, sige, mag-stratify ako, pero damihan ko ngayon yung number of points na gagamitin ko. Halimbawa, meron akong budget. Ang budget ko ay 25,000 points. Dahil kakaunti naman yung paggalaw o yung deviations dun sa function from 0 to 2, dito, gumamit lang ako ng 100 points. Tapos kung saan malaki yung paggalaw o malaki yung variations dun sa paggalaw ng function, dun ko i-allot yung 24,900 points remaining. So dun ako pipili ng 24,900 random data points kung saan nangyayari yung action dun sa function. All right? So if I do this, I still get 25,000 points, but I focused my samples on the interval 2 to 4. And if I do that, okay, tingnan natin yung result. The result is this, 0.38, all right, which has a relative error of just 4.91%. Okay? So medyo maganda na siya, all right? And of course, siguro sinuwerte lang ako dun sa pag-draw, pero if I choose my random numbers, or if hindi pala I choose my random numbers wisely kasi wala tayong hold sa pagpili ng random numbers. But if I will design a clever way of how to select the random numbers or a scheme of selecting these random numbers, then I will get better and better approximation. All right? Kaya pag nagre-research kayo, kung alam nyo, kung may idea kayo, ano yung curve nung function, then doon kayo mag-stratify. Halimbawa, COVID-19 cases, yung gusto nyong i-model. Alright? So, alam nyo na siguro, kailan ba? Starting from March 2020 hanggang, say, August 2020, marami tayong cases. There's a big spike. So, pwedeng i-allot nyo yung maraming data or yung maraming random points over that interval rather than the previous few weeks wherein we have reported less numbers and less variations in the number of cases. All right, so para matulungan natin yung mabagal na convergence ng Monte Carlo simulation. All right? So that's my example for the one-dimensional case. And as I've mentioned, mag-overtime pa siguro ako mga 10 minutes pa. You can leave, but you can also stay. Do you guys have any question before I continue? All right, wala naman. So let's consider a two-dimensional example. Okay, an integral in 2D. All right. So ang function ko ay function of two variables. So siya ay si y sine x minus x cosine y. And we will be using Monte Carlo simulation to estimate the integral of the function little f over the y interval -4 to 5 and the x interval -5 to 4. Now, we can do the computation by hand. Ito lang yung integral niya. All right? And it's approximately equal to -3.50 para lang magkaroon tayo ng idea kung maganda na nga ba yung points na nagamit natin. And then we have four experiments here to perform. Isa-isahin natin yung sagot dito sa apat na experiments na yan. All right? But in all of these experiments, same formula ng Monte Carlo simulation yung gagamitin natin. V over N times the summation of the function values evaluated or the function evaluated at random points. All right? So ano yung size ni omega? Si omega ay yung rectangle -5, 4 cross -4, 5. So ang volume niya ay 81 o yung area niya ay 81. This is length 9. This is length 9. So you have a square of side length 9. So ang area niya ay 81. So si V ay 81. Si capital N, siya yung number of points used. Tapos summation ng function values, yun yung formula natin para dun sa integral. Right? Now, the first experiment asked us to perform Monte Carlo simulation using 100 points. Okay. So, ito yung 100 points na nabunot ko. Right? Tapos, nilagay ko sila or sinuperimpose ko siya dun sa graph ng function f. So, I generated this using MATLAB. So, pina-plot ko yung three-dimensional surface formed by y sine x minus x cosine x over the integration interval. Ano ang integration interval? -5 to 4. So si x ay from -5 to 4. Oops. Tapos si y ay from -4 hanggang 5. Alright? So nangyari ay, parang kinuha ko lang yung average ng volume ng mga cubes. Kasi yung integral, yung double integral na nandun sa problem, siya yung volume ng solid formed using the function f or the surface f as the upper boundary and the xy plane as your lower boundary. So yung integral na ina-approximate natin, siya yung volume nung solid under this curve, but above the x-axis. So parang nakapayong. Imagine niyo ito yung bubong nung bahay natin na rectangular yung base from -5 to 4 and then from -4 to 5. Yung volume na yon na nasakop nung nabubungan ng function f, siya yung ina-evaluate natin. Tapos sa bawat isang draw, pumipili ka ng isang point na naglalay doon sa surface, right? So limbawa, ito yung i-analyze natin. So kung ito yung gagamitin natin, ito yung magsiserve as the height, yung function value na yan, f of xi yj. Alright? Tapos kukunin ko yung volume nung cube with that as the height and as the rectangular integration interval as the base. So kukunin ko to. Okay. Ito yung integration interval natin. Siya yung magiging base. Tapos ito yung magiging height. Kukunin ko tong cube na yan. Yung volume ng cube na yan, yan yung approximate ko para dun sa area or para dun sa volume under the surface. So siya yung magiging approximate ko using 1 point doon sa definite integral na ine-evaluate natin. Of course, this will be a big miss kasi marami tayong ma-under o ma-overestimate, right? But imagine using 100 points, I will calculate the volume of 100 such rectangular prisms, right? And then I will average them out. And the law of large numbers says baka naman maganda na yung makuha mo kasi gumamit ka na ng 100 points. But of course, you should use more points in order to get a better approximate. Okay? So nakapili na tayo, endpoints yung gagamitin ko. Yung second step sa Monte Carlo simulation ay pumili ka ng 100 data points. Okay? So pipili tayo ng data points from -5 to 4, cross -4 to 5, randomly distributed. So random number yung X component, random number yung Y component, I should get 100 ordered pairs. Yung 100 ordered pairs na yon are represented by the blue dots over here. And you see that they are well spread over the interval, over the integration interval, di pala, integration region omega. Right? So pag kinuha ko yung average ng mga volumes ng mga rectangular prisms formed by these data points, all right, ang nakuha ko ay 7.83, which has a relative error of 323%, which is bad. It's a big miss, all right? Kasi nga, 100 points lang yung ginamit ko. Tapos, oscillatory pa yung function. Napaka-wavy niya. So, I don't expect to get good results using 100 points. And you see na kahit 100 points yung ginamit ko, the promise of Monte Carlo simulation is that we'll get 1 over root n na error proportionality constant. Here, n is 100. Ibig sabihin, dapat 1 over 10 yan, or about 10%. Pero nakuha kong error is 323%. Right? The reason there, nasa bababang dimension pa tayo. So, hindi pa ganun kabilis yung convergence ng Monte Carlo simulation. And it's a hit or miss method. So, you can think of 10% as the optimistic error constant. So, at best, we can get around 10%. So, if your draw using 100 points will give you an error of around 10%, then you have a good draw. Pero this is obviously a bad draw kasi nga 323% yung relative error. I tried doing this experiment several times and I guess I got lucky one time and I got a relative error of 18%. Okay, which I say is a hit considering that the best I can get is around 10%. Okay? So 100 points is not enough. So maybe let's increase it a little bit. Oh, not just a little bit. Gawin nating 100,000 points yung gagamitin ko. Nag-perform ako ng 5 Monte Carlo simulations na tigwa 100,000 each yung points na ginamit. Ito yung mga nakuha kong results. Okay? So of course, the best one here, you see here, I still get 17% error. Here I still got 19% error. Here I got 2% error, which is good. But again, if you don't have any idea about the relative error, and that's always the case because we don't know the exact value. That's the reason why we are approximating the integral, right? Kunin mo na lang yung average nito. And that will give you the middle ground among these 5 results. Okay? So, makikita nyo, yes, 100,000 yan. Okay. Tapos, dadamihan ko pa kasi marami akong time. Tapos, mabilis lang to. Kahit 100,000 points ang ginamit, function evaluation, it will be finished in a blink of an eye. Lalo na kung pang-gaming yung laptop na meron kayo. So, kung malaki yung RAM nyo, 16 gig na RAM, or kung ilan na bang cores ngayon ng mga computers. So, kung ang laptop nyo ay quad-core, you can do parallel processing and ask your computer to do 4 parallel calculations at the same time. Sana pala makapag MATLAB clinic ako para mabigyan ko kayo ng idea paano mag-run parallel para ma-optimize nyo yung 4 o 8 cores ng mga laptops nyo. Bawat isa kasing core ay pwede nyong i-consider as 1 CPU. So kung marami kang irarun na simulations o maraming parts in program, kung meron kang for loop or gagawin mo tong Monte Carlo simulation several number of times, pwede mong ipasa yung trabaho sa bawat isang core ng computer mo. So it's as if having 4 different laptops running the same experiment but with different random numbers at the same time. Dahil 4 yung cores ng usual computers ngayon, pwede niyong pagawa sa kanya 4 na simulations at a time. So makakasave kayo ng oras. Tapos kung meron kayong gaming laptop na mataas yung GPU Alright? Yung GPU ngayon, hindi na lang ginagamit sa gaming. Pampaganda ng graphics sa pagdodota o sa paglolol nyo or kung anong RPG yung nilalaro nyo. Pag hindi ka naglalaro, pwede mong gamitin yung GPU ng gaming laptop mo as additional cores. So mas mabilis ngayon yung simulations and usually you can run hundreds of experiments at the same time using your home computer or your gaming laptop. So, ganon. Ginawa ko yung Monte Carlo simulations, of course, parallel yan, kasi 1,000 times ko siyang ginawa with 100,000 points each. And you see the parang napakalaki ng project na to. 1,000 beses ako nag-run ng Monte Carlo simulation na tig 100,000 points yung ginamit. I got on the average, or the average estimate is this, which has relative error of around 4.59%. That's good enough. That's 4.59%, but still that's an underperformance with the error proportionality constant, which is 1 over square root of 100,000. So that would be 1 over 100. So dapat around 1%. Actually, okay na pala siya. So around 1%, 1,000 simulations with 100,000 points each gave you an average of 4.59% relative error, which is within the same order no expected natin, the 1 over root of capital N. All right? Of course, if you want better result, you can push it to the extreme and try my fourth simulation here. Ang ginawa ko naman ngayon, nag-run ako ng Monte Carlo simulation na gumamit ng 10 million points. Imagine, 10 million points. Sa Newton codes at saka sa Gaussian quadrature, magrereklamo na yung computer nyo na 1 million points, what the... yung papagawa mo sa kanya. Pero sa Monte Carlo simulation, it's just 10 million function evaluation, taking the average of that 10 million points, tapos i-multiply ko lang ng 81, which is the size of omega, all right? Ang nakuha kong relative error ay 2%. And you see how yung unang run, 2%, right? That is already a hit for me. Pero kung makikita niyo yung napaka-spectacular na mabagal na convergence ng Monte Carlo simulation. Gumamit lang ako ng isang daang libong points, nirun ko siya ng 1,000 beses, nakakuha ko ng 4.59%. Ngayon, gumamit ako ng 10 million points, pero halos nakalahati ko lamang yung dating relative error. Bumaba siya sa 2%. So, how many times more yung 10 million than 100,000 and yet na-divide lang by 2 yung relative error. Talong-talo siya ng composite Simpsons. Kasi yung composite Simpsons, order h to the fourth yon. So kunin yung 10 million over 100,000, tapos erase nyo yun to the, 100,000 over 10 million, erase nyo yun dun sa fourth power, yun dapat yung nabawas dun sa relative error kasi order big O of h to the fourth siya. Pero dito, na-divide lang by 2 yung 4.59, bumaba siya ng 2.04. Alright? So napakabagal talaga ng order of convergence niya. Alright? Now, I run this simulation a couple more times, or actually several times, and I got results with relative errors between 0.50% and 2.89%. And I guess using 10 million points, the worst that I got is 2.89%. Probably I was just very lucky in my draws, pero I guess that's reasonable. Na 10 million points, at worst, around 3% lamang yung relative error. So the lesson here is Monte Carlo simulation is a very simple process. The theory behind it is very basic. All right. Gumawa ka lang ng experiment a lot of number of times and you're good. Now, it's a hit or miss method with spectacularly slow order of convergence. So what you can do is to increase the number of n from the get-go, perform several instances of the simulation, take the average, and take that average to be your approximate. All right? So yun yung idea ng Monte Carlo simulation. Yun nga lang, kailangan yung bantayan yung memory ng computer nyo. Kasi kung offline kayo nag-work, usually kung 8 gig or 16 gig yung RAM ng computer nyo, baka you cannot go past more than 100 million number of points to be used. Kasi nga medyo ano yan, sinisave ginagamit ni MATLAB o ng computing software nyo yung RAM ng computer nyo to store results of calculation kasi kailangan niyang meron siyang access sa kanya randomly. Kaya random access memory yung ginagamit niya. Tapos, pag masyado nang malaki yung data, titigil na si MATLAB kasi sabihin niya, hindi na kaya ng computer mo na i-store yung number of points na pinapagawa mo sa akin. Wala na akong paglalagyan ng data na gagamitin ko dun sa computations later. But that's more of a hardware problem. Siguro in a more technical computing class, we can talk more about it. Pero I think the focus here is the method itself, and I hope it is clear to you how to implement Monte Carlo simulation. All right. So I guess that's all that I want to say today. Okay, buti hindi ako aabot ng 1.5 hours. But do you guys have any questions? All right, so I hope may napulot kayo kahit konti sa discussion today. So I will upload the lab exercise probably later today or early tomorrow. Kakatanggap ko lang ng lab exercise, babasahin ko pa siya, and I have a meeting right after this. So yeah, it might take me at least tonight or early tomorrow to upload it. So makita niyo na siya before yung Monday. All right? Okay, so if you guys don't have any questions, then thank you all for coming today. And actually, it's a nice thing to see you again, at least virtually, after ilang weeks, ilang days ba tayo hindi nakita-kita. I think it's almost, it's actually more than a week. So it's nice meeting you today. So I hope you guys enjoy the rest of the day, your weekend, and let's see each other again on Wednesday to talk about the project. Oh, by the way, before I end the meeting, nabanggit ko na nga ba yung Google Form? Nag-send ako through Canvas announcement. I hope you saw this in your emails or in your Canvas notifs na sa project, pwede kayong mag-group, bumuo ng group of at most 4 members. You can do it solo if you are more comfortable doing it solo. Pwede naman by pair, pwedeng 3 kayo or pwedeng 4 kayo sa group. It's up to you. You can form a group within your lab section, pwedeng sa kabilang lab section, pwede rin sa kabilang lecture. It doesn't matter to me as long as more than 4 members. As long as less than or equal to 4 members. And then if you want to be part of a group, but you don't have any idea or you don't have any group mates yet, kindly answer the Google form I sent via Canvas. So para malaman ko kung na gusto nyo magkaroon ng ka-group pero wala pa kayong ka-group. Tinanong ko rin doon kung ilan yung gusto nyong mga number of members dun sa group. Actually, preference lang naman yung kung ilan. Titingnan ko, I'll try to do my best to give you your preferred number of members, pero depende dun sa mga magsasagot ng survey, right? So I hope you get you fill up the survey by Thursday next week so that I can release the grouping by Friday para mapagsimulan nyo ng mapag-usapan yung project before you go on Christmas break. All right? So that's it for today. Thank you guys for coming. Again, enjoy your weekend. Let's see each other again on Wednesday. Bye, everyone.
Thank you po, sir.
All right.